Right, so we're interested in continuous distributions. So far we've really been just looking at discrete ones. So let's just compare the difference between the two. So we'll have a look at this one. Simply a probability of tossing two heads, basically. So the number of heads tossed. So the only outcomes we could have 0, 1 and 2 and the associated probabilities. Remember we said random variable, that's x. Probability function, x equals x, or probability of x. Now, I'm going to introduce this other one, the cumulative probability function. So cumulative probability function, probability of x is less than or equal to t. So function t, probability of x is less than or equal to t. T goes from, now you'll notice I've put a there. I'm basically meaning the start, because depending on what the first outcome is, it would change what a would be. I suppose you could think of it as minus infinity if that was possible. But because it's cumulative, you're starting from whatever the minimum value is, going up to whatever x happens to be for this problem. So for example, function 1 would be the cumulative up to 1, so it's a quarter plus a half, 3/4. So cumulative probability function, also known as cumulative distribution function. So you could see either term for that. That was a discrete variable, of course. For a continuous random variable, a probability function doesn't exist. Let me show you. Consider the random variable x, and x is going to represent the height of adults. So that would be a continuous variable. So between any two values, I've got 170 and 175 centimetres, there would theoretically be an infinite number of possibilities, because you can keep breaking the measurement down and down and down. So therefore, the probability that our random variable is 172.4 must be 0. Sounds weird. There's no chance of that happening. But here's why. Let's say there are 23 people of a height 172.4. Well, the size of my sample space, it's continuous. So therefore, there's an infinite number of possibilities. So if I was to work out the probability, it would be 23 over the size of the sample space. Well, I can't put it over infinity, so we'll say the limit as n approaches infinity. Well, of course, we know that's equal to 0. So weirdly, even though we've got 23 people that are of height 172.4, the probability that someone is 172.4 is 0. I mean, that's if we treat it like we do with discrete. In a continuous distribution, the probability of any single value is actually 0. Weird. So what we do is we look at the relative frequencies and we use classes. Remember back in discrete data, we use class intervals. By doing that, we can turn continuous into discrete, because now we can say which class it drops into and we have discrete values. So let's use this as an example. The amount of time we're waiting for a ski lift. We're down the snow, we're waiting for a ski lift. Now, of course, time, again, would be a continuous scale. So we're going to break it up into different classes, intervals. 0 to 1 minutes, 1 to 2, 2 to 3, 3 to 4, and so on. There's our relative frequencies of each of those happening, and the cumulative relative frequency as well. So if I wanted to know, remember, the probability of a single thing happening would be 0. So what we tend to look for is, what's the probability that it is in this range? So what's the probability that it's between 1 and 3? Different ways we could do it. I could use the relative frequencies. So if I use the relative frequencies, I could say, well, it's 0.196 plus 0.210. 1 and 3 would cover those two classes. So it must be those two added together. We get a probability of 0.406. I could use the relative frequency histogram. Okay, there's the histogram. Well, I've also drawn the polygon as well. But in this case, once again, because the width is equal to 1, just as we saw yesterday, it's actually going to be exactly the same as adding up the probabilities. So we'll get the same answer. If I use the polygon, And that's where we would estimate using the trapezoidal rule. And that one, I get a slightly different answer, but 0.40575. Use cumulative relative frequencies. So now it would be whatever the cumulative of 3 is minus the cumulative up to 1. And that would leave you with what's in between 1 and 3. But what if we wanted to find this one instead? If I wanted to go in between 1.5 and 2.5, now don't let that table up the top fool you, because remember they were just the class centers of the information. Well, if I reduce my classes now to a width of 0.5, I then should be able to find that range. So I've now broken it down to intervals of 0.5. And again, we could use any of those methods before. We could use the relative frequencies and we get 0.207. The relative frequency histogram, but this time when I use the histogram, note the width of the histogram is no longer 1. So I need to multiply the answer by 2. Why is that? Because we know the sum of the areas of all those rectangles has to equal 1, because it's the sum of all the probabilities. But if I was to find the area of all of those, it would add up to be a half, because it's going to be a half times all the probabilities. So it's a half of the sum of probabilities, it'll be a half. I need that to be 1, so we correct it by multiplying it by 2, and we come up with 0.207. We could use the frequency polygon, so again, estimating using the trapezoidal rule, come up with a slightly different answer on that one. We could use cumulative relative frequencies, again using that idea of, I'll go 2.5 and subtract the 1.5, leaving me with in between 1.5 and 2.5. What would happen then if the width of each class was actually 0? Now obviously it can't be 0, but as it approaches 0, then the area under the polygon now would actually approach the area of the histograms, because it's becoming like our discrete one that we saw yesterday, and ideally that's what we want. That will equal function B minus function A if I use that last method. So the difference in the cumulative distribution function, and that's the key idea we're going to need. So let's now talk about a thing called a probability density function. And what it is the equation of that polygon. Because now, if you're limiting the height, the width, your class interval, to be 0, you're no longer going to have a polygon which is just like a dot to dot. You're now going to have a curve. And we can find the equation of that curve. It will have the following properties, of course. The function will be greater than or equal to 0. And now, this explains why on earth are we looking at statistics in a calculus course. Right? And now we know why. Because we just said the probabilities was the area under the curve. Well, the area under the curve is integration. So if I integrate from, well, if I was to get every possible value, minus infinity all the way up to infinity, it must equal 1, because it's going to cover all the probabilities. Okay? So if I now want to find in between A and B, then I integrate from A to B of the function of that curve. So a bid's made in an auction for a real estate property in millions of dollars. So this would be a continuous. Theoretically, you could keep breaking it down. Well, could you offer less than a cent? No, maybe not. But it can be modelled by this particular function here. And you'll usually find that it doesn't end up going from minus infinity to infinity. They might say, well, it's in between 1 and 4 as our possibilities, and everywhere else we're just saying the probability of it happening would be 0. Find the value of k. So what do we know? Well, we know all the probabilities from minus infinity to infinity. When we integrate, we must get 1. So therefore, the integral from 1 to 4, because everywhere else we know there's going to be a probability of 0. So we only have to integrate from 1 to 4 for this question. And this should equal 1. So now we just solve the integration problem. So add 1 to the power over the power, k ends up being 1 on 27. So we found our function. So now what we're interested in is, what is that cumulative distribution function? The cumulative distribution function will be 1 on 27, because we now know what k is, the integral from 1, we're starting from 1, but we're just going up to x, whatever value we're interested in looking at, of 16 minus x squared. So calculating that one out, there's our function. If I wanted to write it as a step function, what I now know is that, well, before 1 there's a probability of 0, then between 1 and 4 it would be our cumulative function, distribution function. But after 4, probability must be 1, because we've now covered every possibility. And so cumulatively we're not adding any more on, so it'll stay as 1 after 4. What's the probability that a bid of more than $3 million will be made? Well, we're now saying, what's the probability of our random variable being greater than or equal to 3? Well, the way our formula is set up, we want less thans, not greater thans, because we're going to go function b minus function a will leave me what's in between. But I know all the probabilities add up to 1, so if I take away the probabilities going up to 3, I should be left with the ones that are after 3. So subbing it into our function, we get 1 minus 70 on 81, so a probability of 11 on 81. So how do we now go and find information with our cumulative distribution? How do we find the quartiles? Well, Q1 then, we can work out via this little equation. Minus infinity up to Q1 must cover a quarter of the probabilities. So we know that that integral must equal a quarter. If I want to find the median, then the probability must be a half. Q3 then, the probability would be 3/4. So here's a probability density function, 1/9 x squared, it's 0 everywhere else. So find the median. Okay, well I know the sum of the probabilities would be a half. Let's solve it. So add 1 to the power over the power, and we get, well, it's a lovely expression, so there it is. 3 on the cube root of 2 would be the median for this particular distribution. 2.38, we're probably not going to leave it in stats as 3 on the cube root of 2, we'd probably approximate. How would we find the mode then of our distribution? Well, the mode then will be, because think about it, we now have a function for the curve of that polygon. The mode is the greatest frequency. So we want to know what is the maximum value of that function. But be careful, because remember, the extremities of our domain might possibly be the maximum value. So we want to find when the stationary point, so first derivative is equal to 0, and it's concave down, so the second derivative is less than 0, but as I say, you might want to check the global maximum, could it be at either end of the domain. So let's find the mode of this one. Now, of course we don't have to use calculus for this one, that's a quadratic. I can use theories about quadratic here. It's an upside down quadratic, so I must be talking about the vertex of that parabola that we would end up drawing for the function. So we know what happens on the axis of symmetry, so the mode is 1. So the mode would be the x value, not the frequency of it, but so it's the x value I'm looking for, the axis of symmetry. Okay, now we're starting to have some fun with stats.